Earlier I was thinking I will start a new topic, but I will continue and complete things on friction and things we have done earlier in the course. So, first of all, the first type of problems which I like to take will be frictional forces on collar bearings and discs. I gave a brief sketch of it last time, but let me do this problem in detail, and at least it tells you how to deal with friction when you have a contact where you are making some assumption about a distributed force on the contact. You are not assuming it that the normal reaction is acting at a single point. So, let us see some of this. So, these type of friction, there are two type of problems typically. We have a circular rod which is rotating, or there is a tendency you want it to rotate. An axial force P is applied on the rod, and this rod let us say is in contact with the ground. So, this is something like you are pushing a rod and at the same time you want to then start to rotate it. So, therefore, here neglecting this small part, there will be friction acting from the bottom, and there may be problems where this part, if this length is long enough, then frictional force will also act, or contact force will also be there all along the side. Okay. So, this is the type of problem that you are applying a force P. So, this in fact maybe this is probably causing a bit of confusion. Sorry, let me remove this. There is a, and I will put this with a force P which is applied, and of course there is a moment M. So, what we would like to know is, if the coefficient of friction between these two surfaces is mu, then how much moment needs to be applied so that this will just start to move. So, this is what we will call how much frictional moment has to be applied to overcome the moment because of friction. And as I will show to you, in this case, in a contact like this, friction does not cause a force on the body. The net effect of friction will be a couple. It causes a force, but then an opposite force comes from the other side. So, the net effect of friction will be in form of a couple. So, this could be one type of contact. The other type of contact, so this is what we would call a disc type of contact. Now, it is possible the second surface may also be moving. Here I have shown the surface with the ground, and that happens when in the case of an automobile when we have a clutch. The clutch contact, we have two wheels which are there, two discs which are in contact, one of them rotates and that causes the other one to rotate because of friction. So, those problems would be just a simple extension of these type of problems, a different scenario, but the methodology is the same. In this we also have what is called a collar bearing. In a collar bearing, what we have is, there is a rod like this which is basically going here, there is a surface, and then on this surface there is a collar, and this is what we call as a collar bearing, and in this case the contact between the bearing and the rod is extending from R1 to R2. So, it is an annular contact, it is not a full disc contact, it is a contact starting from R is equal to R1. So, this is the surface where this is the rod, on the rod we have a collar, and it is the collar which is in touch with the ground. So, that means the rod rotates, the collar along with it rotates, and this surface area of contact will be pi times R2 square minus R1 square. So, that is the other scenario. So, these are the different scenarios. Then of course, you could have contacts, and the contact pads need not be over the full circle. There could be 4 pads symmetrically placed, things like that. So, all these would come under the same category of problems. So, now here what we are given is, what we want to find out is that the rod is held by an axial force P, and what we find the moment M needed to turn the shaft, or in other words, the axial moment needed to overcome the frictional couple. So, in all these problems you have to look at the area of contact. So, let us look at the left problem, that is the problem of a disc contact. So, here if I look at the top view, the area of contact is a full circle, and what I do on this area of contact is that I will choose a differential element of area on the area of contact. Now, if I have a full circle as the area of contact, what sort of a differential element do I choose? So, I will choose an element, let us say from some reference position, it is at an angle theta, and this is basically the element chosen is a sector of a circle it is located at a distance r, and this dimension is dr, and the angle which I have here is d theta. So, in all these problems, locating the proper element is the key to solving the problem. Okay. So, therefore, this is what we have. I choose a sector of a circle. So, in this case of radial extent dr and subtending an angle d theta located at a distance r from the center. So, in this case, when I do this, so dA is r is actually, let me again reword it, put it properly, dr times r d theta, because dr is the thickness of this element, r d theta is the circular curve. So, therefore, this elemental area dA is equal to dr multiplied by r d theta. Is that clear? So now once we have this, then let small p be the normal force per unit area acting on the surface. So on this element, the normal force which is acting, now normal force will be perpendicular to the contact. This is, I denote that as small p. The symbol p, small p has been used because it in some sense denotes pressure. It is a normal force per unit area. Normally we use pressure for in a fluid sense, but so therefore that's why I use the symbol small p, because it represents the pressure on that element. Okay. So now on this element, the total normal force, let the normal force on the element will be equal to, let us write this as dn. Wherever I am using a symbol small d, it means it is referring to the differential element. So dn is equal to p multiplied by dA. So this will be p times r dr d theta. Okay, is that clear? This is the normal force, and in what direction will it act? As shown, if I refer to this figure, in which direction will be dn acting? It will be perpendicular, that means it is coming out of the paper, either inside or outside, depending on where your, if the rod is placed inside, then you will be, then the force is coming from that side or this side. So it is perpendicular. Now let us say this is the direction of motion which we want to impart to the whole disc. So then in which direction will friction act? Friction will be acting in the opposite direction. So on this we will have a force of friction which I will call as dF, because this is trying to rotate in the other direction. So friction force will try to oppose this. So this will be the direction of dF. Okay. Now what will be dF in terms of dn? It will be mu s dn when it is about to slip, otherwise it will be less than that. Okay. So we keep that in mind, the dF will be just mu times dl. So this is how we work out these contact problems, but just before we go to that, this is dn. Do we know what the integrated form of dn is? What is the total load dn? If I sum over d on the entire surface, what will I get? I will get capital P, because that is what has been given as the axial force which is acting. So what I know is integral dn on the total area, or let me again, integral dn, I'll first erase this, on total area, this is equal to capital P. Let us do that. So that means what we will have is P will be equal to integral of P r dr d theta, and since now there are two differential elements, I will put a double integral, one for r, one for theta. Now I will need to know how is P varying, and this typically is something which will be given to me. I may be given that P is constant. If P is constant, I will just pull it out of the integral. It may be given that P is what? The pressure which is acting. It may be given that P varies like 1 over R. So then I will have to put P as, or K upon R. If it is proportional to 1 over R, I will have to put on K as K over R. And there will be some data given in the problem, or which we will have to assume, which will help me calculate the value of K. Let me say I know P at a particular R. So then I will work out the value of K. So therefore this P, something more about this has to be specified, at least either in the problem, or if you are working in real life, then you have to make some assumption that okay, P has this form with R which has to be closer to real life. let us, I take the simplest example in the class. So, I will take P as constant. So, if I take P as constant, then what will happen is this P will become equal to P times integral r dr d theta. Let me just do it like this. Now, what are the limits on, if it is a full circle, then theta will go from 0 to 2 pi, and if the pressure is not changing with theta, there is no change, then this integral over d theta, this part will just become 2 pi, and then I have integral r dr, and r dr will go from either 0 to r. So, r goes from 0 to capital R for disk, and it goes from R1 to R2 for collar. Okay. And so, this becomes equal to P times 2 pi times r dr will become r square by 2. And so, what we get is small p is equal to capital P, and actually I need not have done this integral. If I told you that this P is constant, then you would have directly said the total force divided by total area of contact is nothing but pressure. So, you would have got this without all this hoopla about the integral. Is that right? But why did I do the integral? It helps me in the next part. Now, let us find out the frictional couple. So, here we have worked out the pressure, and the reason I have done this is it may be P had some form of R. If P was a function of R, then it would have come in this integral, and then P would have been inside. You would have got P of R, r dr, and then given that form of R, you would have integrated accordingly. So, it could have changed also. So, that is why I did it in this way, and maybe I will take an example which will further clarify this. So, this is small p. Now, let us go back to this picture. Now, friction force is acting as I showed in the arrow in this direction. So, what is the total force of friction? So, let us first write what is dF. If friction is acting like this, then friction force is equal to, if I write on this small element, it will be equal to mu s times dn when just about to slip, and if it is actually rotating, it will be mu k times dn. Okay. Now, what is the total frictional force on this area of contact? If I see, and as somebody has already pointed out, if I look at a sector which is exactly opposite to this, on this sector friction force would be acting in the other direction. Now, if I have to add up the total force due to friction, then it will be 0. But what friction is doing is, it is forming a couple, because about this point there is a moment, about this point the moment is in the same direction. So, basically friction is not causing a force, it is forming a couple. Is that clear? So, that is what we do here. So, let us then complete this. So, dF I can write it, but actually dF does not help me too much. What I need to write is the moment on this area. So, moment on this area will be equal to mu s r times dn, and dn I have already written. What is dn? dn is p dA. So, this will be equal to mu s multiplied by r times dn. dn is p multiplied by r dr d theta. So, I am just writing dn, just copying that from the top. So, therefore, the total moment will be integral of mu s times p r square dr d theta, and once again r goes from, in our case, 0 to r, and d theta goes from 0 to 2 pi. So, therefore, this becomes equal to mu s times p times r cube by 3 times 2 pi. In this case, because things were not functions of r and theta, I could just write it directly like this. Otherwise, you have to be careful. You have to, if r is a function of theta, then you have to put in the functionality of theta also, and then work out. Okay, and this p, this is small p, so this is equal to mu s times p divided by pi r square into r cube by 3 into 2 pi, and you will get your answer. Okay, so this is how we find the frictional couple. Is that clear? Now, as I said, different problems of this type could have different geometries, and there could be different scenarios of these type of things. Let me pose another problem. Are there any questions on this? No. So, now then let us move to example 2, let me say. Example 1 was this problem. Here what we have is, and a 200 millimeter diameter post is driven 3 meters into sand, for which mu is equal to 0.2. If normal pressure acting around the post varies linearly with depth, as shown, find the torque M required to overcome the frictional torque so that the post can be rotated. So, let me draw the complete figure. There is a post which is dug in the ground, maybe it could be slightly higher up, and then in this case what is given to us here is that the ground all along on the post is applying a pressure, and this pressure is given that it is, this thing is 3 meters inside the ground. So, this is a sort of a practical problem. You could think that there is something which has been buried in the ground and you need to take it out. So, therefore, you give it a twisting turn so that you can start then pulling it, and what we need to find out is how much moment should be applied so that it could be pulled out. Now, what is given to us is the normal pressure which is acting on the post. It varies linearly with depth, and as shown. So, let me draw the complete figure, that at this point the pressure is 0 and this pressure varies with depth, and in the problem we give the value of the pressure at the bottom is given to be 600 newtons per meter square. It starts from 0 and at a depth of 3 meters. So this is 3 meters and this diameter is given as 0.2 meters. Okay. Now you'd say, where would such a thing come? You know, is anybody from Jaipur? No. There's a museum of Indology in Jaipur where there are supposed to be spears belonging to Rana Pratap's time and things like that, which he has kept there. And you know how does he make those spears? He takes a new spear and he digs it in the ground and keeps it there for 1 month. After that he pulls it out and puts it on the wall of the museum that this is a historical old spear which was used by Maharana Pratap. So when you go visit that thing on the backyard, you will find many spears dug in the ground. So now he has to do an exercise like this to pull that spear out. Okay. So that is the sort of an application where this problem would be used. Okay. So now here, see again it's a problem of normal force being given. You have to find the moment because of friction, but it's in some sense similar to the previous problem, but the geometry is different. What is the area of contact in this problem where the normal reaction and friction are acting? It is the surface, lateral surface, what they call, of the cylinder. So now what you have to do is, you have to choose an element of area not on the flat surface but on the lateral surface of the, because you have to identify the contact area. The contact area is the curved part of the cylinder. So on that you have to choose a small element of area. Now what you may also realize is that this problem is axisymmetric. That means the pressure which is given is varying with depth, but all along the circular cylinder it is same. Nothing is given, so we'll assume it's same, or maybe I will say it is axisymmetric. Axisymmetric means things don't change with theta. So the pressure, since the pressure distribution is the same all along, then I can choose a ring as my elemental area instead of choosing a part of the ring. If the pressure was also changing with theta, then I would have had to choose a curved part on the of length delta z. So what will be my elemental area here? Elemental area will be a ring. What will be the length or of that ring? It will be dz, and where will it be located? At a distance z from either the surface or from the bottom. Depending on what your problem is, you choose it like that. So that means here, and that is the key thing, that to work this problem out, the elemental area which we choose, this is a ring of length dz located at a distance z from surface. Why do I choose a, that means I am choosing, so this is your surface, I go at a distance z down and I am choosing a ring of dz, let this radius be r. So now the area of contact is equal to two pi r dz all along this. Okay. So now on this, the pressure is varying linearly. So this is, let me be very clear, this is pressure, this is equal to kz, and what is the value of k? Since P is equal to 600 newtons per meter square at z is equal to 3, this will mean k is equal to 200 in SI units. Okay, so I put 600 is equal to k times 3, so 600 by 3 is equal to k, so get k is equal to 200, and this I will not write the units, I will just say SI units. Once I have this, then let us directly write the moment. The frictional moment, again if a moment m is being applied like this, friction will be in the opposite direction. The frictional moment will be, what is the force of friction? Force of friction will be mu s multiplied by P times dA. This is the force due to friction, and to that this is what we can call as the moment arm, or the distance from which the force is acting. Now you realize, as opposed to the previous problem, r is constant, because everywhere it is at the same r. Now you are not integrating with respect to r, you are integrating with respect to z and theta. So this is what we have, the total moment which I will get on this ring dm will be equal to mu s into p into dA into r. So once I have all this, actually it is quite straightforward then. So m will be equal to integral mu s into p into dA. dA I have already written as 2 pi r dz into r. And but now, so this will become equal to mu s into 2 pi into r square, and then integral of p, p was 200 z dz, z goes from 0 to 3. Okay, and you will integrate this, that will give you the moment. Okay, is that clear? So this is, so in these contact force type of problems, you have to be careful. You try to work out the proper area and then work out the where the frictional force is acting, what type of moment is it causing, choose the proper elemental area, find the moment on that, integrate over the entire surface, and you will get your answers. Is that fine? Okay. Now let me take an example. What I will do is, the chapter 8 solutions I will put it on the website. I will do that probably soon after the class. All the problems of, so some of them in some groups they have been done, and other groups they have not been done, but I will put it on the website. Also chapter 6 and 7, chapter 6 I will put today, or I think they have already been put, I am not sure, but chapter 7 I will put after, assignment is due today. After that, today evening I will put up the solutions of chapter 7 also. Earlier chapter you may have realized I have put up the solutions on the web. Also the lecture, you people are coming to the lecture, so you probably don't need it, but the video recordings of the lectures also are available on the website. I have sent the link to you in a mail, so you can check that, and that could, I don't know if that's useful or not, maybe later on we will take a feedback on that. Okay. Now let us take another example, and this one is on belt friction. We have we have these three drums or rollers, whatever you may call it. There is a cord which is passing through these three. A weight W is held here. Now, there are certain things which I will specify in the problem, and there is a particular reason why I have taken this problem. Also, let me just, this angle is 45 degrees and this angle is also 45 degrees. Now, let me first write the problem. The maximum tension that can be developed in the belt is 500 newtons. Now, let us see, pulley A is free to rotate and B and C are fixed drums. The coefficient of static friction at all surfaces is equal to 0.25. Determine the largest W that can be lifted. Okay. So, we want to find the biggest weight W which can be lifted when we are given that the maximum value which we can apply or the maximum tension which can come in the belt is 500 newtons. If more than that comes, the belt will break. Okay. Now, also what is given is posts B and C, these are fixed drums, whereas the pulley A is free to rotate. That means there is no friction, it can just rotate if need be. Okay. So, now let us try to analyze. If the weight has to lift up like this, in which direction will this pulley move? The belt has to move in this direction, in an anti-clockwise direction. If the belt moves in the anti-clockwise direction, in which direction will the friction force act? It will act in the downward direction. So, friction force is acting like this. So, if I look at these two tensions, which tension will be bigger? It will be the tension on the left side. We are doing this analysis in our head. Now, what about these two pulleys? In pulley A, which tension will be bigger? Think about it, and that is the key part. You have got some of you have got the right this thing, but what happens in the middle pulley? The middle pulley is free to rotate. So, that means it will not be able to take any moment because it will rotate. So, therefore, the tension in these two sections across this has to be equal, because this comes from the moment balance. That moment about the center of pulley A, if I take, that must be 0. That means the tension on these two sides must be the same. Now, when I look at this, then in which of these will tensions be greater? On the right side or on the left side? On this, once again we analyze that the tension on the left will be greater, because friction once again on the belt will be acting in the clockwise direction. So, therefore, where will the maximum tension in this belt come? It will be at the point P. So, that means given this thing, so what we have analyzed is that the maximum tension in the belt is at point D. So, at this section, this is where the maximum tension will come. Yes. Yes. If we keep, no, but then the pulley is free to rotate. So, then if any moment comes on it, it will start to rotate. So that means it will just because it is free to rotate, there will be no friction which it will apply on the surface. See, friction, when does friction come in? When there is a opposing force. Because there is no opposing force, so therefore there will be no friction which will come here. So it will move. So therefore, when this will be moving, the pulley will also rotate. Pulley will not stop it. So that is why friction will not come there because of this. Whereas in the other two cases, friction will come. So now what we do is, once we realize this, then what is this angle of wrap beta? If I call this as beta, then I have beta will be equal to 180 degrees minus 45 degrees. This is 135 degrees. So this will be, and always we should convert it into radians. So this will be 3 pi by 4 radians. And if I say this is T, this is T1, then I will have P is equal to T1 times e to the power of mu times 3 pi by 4. And because P is given to be 500 newtons, and so this will give me T1 is equal to 277.4 newtons. Then I say, since pulley A is free to rotate, T2 is equal to T1, and this is pulley A, this is T1, this is T2. And then I draw the free body diagram of pulley B. So once I draw the free body diagram of pulley B, I have T2 here, I have weight W. So T2 is equal to W times e to the power of mu s times 3 pi by 4. So therefore we will have W is equal to 153.9 newtons. So this is, we'll work out the numbers. So see, once you have to analyze the problem, once you analyze it, then working out is just punching things on the calculator. Do you want me to put something? Okay, anyway, this will come on the web. So this is how we look at this problem. Now let's talk of another type of problems. Well, there was one more class of problems I did last time. I did an example where something was, there were two contacts on a cylinder, and where the limiting case you have to apply on either one of them. And those problems you have to be careful, you have to apply a friction condition on one, on the other you are assuming no slip. So once you solve your problem, you check that what you have assumed is indeed correct. If that is not correct, that means slip is taking place on the surface where you have assumed no slip, and then you have to redo the problem. So that could be an important part in those type of problems. Now what I would, let's try to think of another scenario and see. In lot of times we make assumptions, we solve problems, and we get ideal situations. and then we realize that probably something is missing in our modeling. For example, when we talk of example of pendulum, if I take there is a pendulum, you leave it, it oscillates. If I go by the theoretical equations, the pendulum should never come to a stop. It should keep on oscillating. Why does it stop? There is air which is causing some friction, and because of which there are some resisting forces to the motion of the pendulum, and that is why it stops. I have a similar example in friction. Suppose you have a wheel which is rotating on the ground, on level ground. Okay, so let's have a look at that, and we'll assume this is a wheel which is rotating on the ground. And let's say it's moving forward. It's rolling without slip at the contact, it's moving forward. If it is moving with a speed v like this, and if it is in equilibrium, then why will it stop? What will happen to the friction force here? So if this wheel is moving with, initially you give it a push, you apply a force so that it starts to move, then you remove the force. Then so in that case the wheel is moving with an moving forward with rolling without slip at contact. Now the question I ask is, why should this wheel stop? Okay, neglecting air friction. Then will it stop or not? Or it could be a things. Do you think that you have some sort of a charkhi or something which you push? Does it stop because of air friction? Or is it something else? So here, that's the what we are introducing here. I am introducing a concept of what is called rolling resistance, and let me explain that. We normally assume that, so the problem is, we say there is a rigid cylinder of weight W moves forward, there is a normal force at the point of contact, now at this equilibrium implies friction force at point of contact is equal to 0. So cylinder should keep on moving. This is W on the cylinder. If I show this is the normal reaction. So if I draw the free body diagram of the cylinder, a weight W, you have a normal reaction. If I put a friction force, that will be 0, because this is just moving with a constant speed. Now actually what happens is, the material, whatever we are assuming it to be totally rigid, but in real life, and this is where, so now as in the pendulum, as I said, it will keep on swinging, and so here even if there is no air resistance, what happens is that this, what we are assuming is a point contact, only if the material is fully rigid. But if it is slightly deformable, then what sort of a contact will we have with the ground? It will be a finite contact, probably not very big, not like a block on a table, but since this is moving forward, the contact, actual contact will be something like, so let me show this, the contact surface is not point as the body deforms, and what we have is if this is the center line, the contact takes place over a finite area, a small area, body is moving forward. As it moves forward, the contact point, instead of being just a point, it happens to be a small area. Now over this area, if forces are acting only in the normal direction, then all of them will pass through the center. So what we can do is, effectively we can consider this distributed force as a single force N, which is at a slight angle from the vertical. So when we draw the free body diagram of this, what we will have is that we have the weight acting here, and the normal force acts at a small angle theta, and this N represents the integral of all these forces, and because each of them is passing through the center, so therefore this integrated N will also pass through the center. Now what you have is, if this angle theta is very small, then there is a component of N which is in the backward direction, and this is what will cause the friction, or which can be treated as a friction force, and this is what we call as the rolling friction as opposed to the sliding friction. So now here I can rephrase the problem as to how much force P must be applied so that the cylinder continues to move at a constant velocity. So that is what how I will do. Yeah, एक सेकेंड मैं लिख देता हूँ पहले. Rephrase the problem. How much force P must be applied so the cylinder keeps moving forward at a constant speed. हाँ बोलो. No, that see, when the cylinder is moving like this, then in which side will more contact come? It has to come in the forward direction. Relative area किस तरफ ज़्यादा deform होगा, खुद सोचो. On which side? On the, if it is moving in this way, that is why it is in this direction. So you have to look at the local movement there. Is it forward or backward? If it is forward, then that part will tend to get crushed. So therefore there will be more of a normal force on that side. So now here what we do is, if we phrase the problem like this, then what we can say is, how much force P should be applied to the center of the cylinder, and now we have the weight W, this is the normal reaction, this angle is theta. If this horizontal distance is A, then what you will see is that P multiplied by this radius is R, R cos theta must be equal to W times A. If I take moments about this point, then I will get W multiplied by A must be equal to P multiplied by R cos theta. Okay, and if theta is very small, then what we have is P must be equal to W times A by R. Now P is the horizontal force, that means P will also be equal to this horizontal force acting on the ground. So the frictional force is W times A by R. If it was sliding, what would be the frictional force? It would be W times mu. So that means A by R is effectively a coefficient of friction when the body is rolling. So in the ideal rolling case, we assume that there is no friction, it's acting just at the center point. But actually this is a one level ahead of approximation, where in rolling also you will have a slight friction, which is given as A by R. Now atypical, now also what you find is in the books, A is given, instead of calling A by R as the coefficient of friction, we call A as the coefficient of friction. So that means the coefficient of rolling friction is written in terms of a dimensional quantity, the length, contact length in meters or millimeters, whatever. So in books you will find when they talk of rolling resistance, then instead of A by R, A is prescribed as the coefficient of rolling resistance, and that is prescribed with a length unit. Okay. So this is, but one thing is very clear, A by, typically when you look at it, so this A, let me write this, A is what is termed as the coefficient of rolling resistance. So it's a dimensional quantity with unit of length. And if I look at some numbers, typically A is equal to 0.5 millimeter for mild steel rolling on steel rail, and this is 0.1 millimeter for hardened steel. What would you expect the value of A for rubber? It will be more. Why? Because it is a more deformable material. The more rigid a material, smaller will be A. More deformable, that means there will be more contact, A will be more. Okay. So if you look at A by R, if it's 0.5 millimeter and radius is typically 10 centimeters, then you will see A by R is very small. And that is why, at least, and these A's may not be very sacrosanct, like what some number these are given in some handbooks, and maybe they vary. But one thing is very clear when we look at this, that the coefficient of rolling resistance will be much less than sliding. So therefore you would like things to roll rather than slide, even though there is a bit of resistance, but that will be much less than sliding. That is one thing. Also we realize it will be, you need a much bigger force P if the weight W is bigger, which anyway is the case, that if it is a heavier object to roll, that you need a larger force. It is not independent of that, but that is what we do. Okay. So with this I think I have completed. I will just do a brief review of what we have done so far in the class. So that is what, let us see. So up till this will be our course for the minor. I will not be giving you any full length problem on rolling resistance. I may test one or two concepts here or there, but there will be no full length question on rolling resistance. Okay. But before that, all friction, up till friction, everything is in course. In friction we have done at least 3 or 4 examples in the class. I will put up the solutions of the homework problem, which are of slightly different type. Most of them are the sliding types, not the rolling type. So I will put those things also. And then now let's just have a brief recap of what we have done in the course so far. So we started with the concept of moment of a force and moment about an axis. So moment of a force we defined as R cross F, and moment about an axis R cross F dotted with D. R was with respect to the origin about which you are taking the moment. So then if the force F is there, then moment of the force is R cross F. And if you have to find moment about an axis, you choose any point on the axis. First you take moment about that point, take a dot product with a unit vector along the direction of the axis, that gives you moment about an axis. So these were the first two concepts which we did in the course. After that, we talked about equivalent force systems. In fact, we also did the concept of a couple. Along with moment, we then did couple. If there are two forces which are parallel and opposite, then they form a couple, and their moment is same about any point in space. Then we came to equivalent force systems, and in equivalent force systems what we saw was, if many forces and moments are acting on a system, what is the net effect of these at any other point? And this we showed in equivalent force systems. We said that if we have to calculate the equivalent, there are two parts. Part A is the force, which is equal to sum of all the forces which are acting on the system, and part B is a couple, which is equal to sum of the moments of these individual forces plus, if there are any couples which are acting on the system, we add all these, that will give you the net couple about point A. Also what we showed was, if for any system we have found the equivalent at point A, we have to shift it to point B, then it will just be the same force and the moment of the net force about point B plus whatever couples you have got here. So add these two, you don't have to do the calculations all over again. So this was the second thing which we did in equivalent force systems. Then we also did the concept of, we did this slightly later, but we did, if the forces are distributed, then how do we find their equivalents? A continuous distribution of forces, a linear distribution, that is what we focused on. We also said there could be a volume distribution or a area distribution. We did not focus too much on area till now, except in today's class, where we actually did the distributed systems what I talked of without saying it was a distributed system, and where do you find the moments. So in distributed forces we found there are two things, where is the net force and where does it act. So those two things were important in distributed forces. So the net resultant force and where it acts. We also did the concept of centroid when we did this, and this also, then we came to this concept of what we called as the simplest resultant. What did we do in simplest resultant? We talked of two cases. If there is a case of planar forces, then we said we can replace all these forces by a single force, but acting along a special line, which we have to determine, then that force will effectively act at the same point. That was the simpler. Second case which we did was parallel forces. Again we said all the parallel forces can be replaced by a single force acting at a specific point now. So now we have to determine both x and y coordinates if we have to find where this force acts. So this is what we did in distributed forces. Then, or maybe not in the same order, but all these could then be applied to the concept of equilibrium of a body. And in equilibrium we talked of, basically what we do is we take sum of forces is equal to 0, sum of moments about any point in space is equal to 0, and with that we are able to find the unknown forces. Here we also learnt how to divide a system into components. If there are more than one components, then internal forces will be equal and opposite. In particular, if there are pin joints, then there will be no moments. So if Rx and Ry are applied on by pin on body A, on body B it will be minus Rx and minus Ry, and so then we can solve problems. Also we learned the concept of a two force member. When we did this, we also learned the concept of two force member. I did not specify or lay too much emphasis on three force member. Your textbook does a bit of it. In fact, even when you see the problems on friction, in some of these the solution which is given will say that all the three forces have to pass through the same point, and that is how they work out the solution. But you can use sigma fx is equal to 0, sigma fy is equal to 0, moments is equal to 0 to get the same answers. You need not use the concept of three force, or you can use, it's up to you. I personally don't find it very convenient to use 3 force, because then you have to locate the point where the 3 forces are intersecting, and that is as much work as doing sigma fx is equal to 0 and sigma fy is equal to 0. Now then we did 2 special cases. So one was doing equilibrium on different bodies and different systems, but then we did 2 special cases of equilibrium. The first case which we did was that of trusses. Trusses were single members, thin members joined, and which we assumed all of them are 2 force members, and then we found out how do we find force in a component of a truss. If it is tensile or compressive, how do we work out the forces? And there we did 2 methods, method of joints and method of sections. Now you can easily realize, if the exam is a 1 hour exam, then I will not ask you to find forces in all the members of a long truss. So typically you would be asked to find forces in members of 1 or 2 members of a truss. So that would be basically the method of sections. Also another thing was we learnt was how to find 0 force members by inspection. So by looking at the members, just looking at the loading, can you say some of these members are 0 force? So this you should be doing, and actually determining that. If I give you a loading and a truss, it should not take you more than 2 or 3 minutes to identify the 0 force members. So accordingly the question in the exam, if any. My exam typically will be of 60 marks. So you can calculate 1 minute to 1 mark. So that is how you could sort of time yourself when you are doing it. But obviously there are some questions which may be worth 3 or 4 marks, but you will be able to do it in half a minute. And particularly that's why I want to give the question that you answer on the question paper itself. Because for example, if you have to do method of sections, maybe on the same figure you can cut the section. Otherwise when you draw it again, it will take you more time. So I am inclined, let me see. If I make a question with only 4 questions, then I will make it in the question paper. But if there are more parts and you are supposed to answer, then I will make you answer in the question paper itself. So this was truss. Then after truss, we moved to sectional forces in the beam. In a beam where we talk of the concept of shear force and bending moments. We cut a section of the beam, and we then the forces exposed there were termed as shear force, axial force, bending moment, twisting moment. How do we find these? And essentially it is nothing but equilibrium. But in simple cases we saw, if we were to draw a shear force diagram or a bending moment diagram, or to write the equations, how to do that. And we worked out some simple rules, or you keep on making cut sections. So now the problems in this, in shear force, could be of 2 types again. One would be to draw the shear force diagram, bending moment diagram of the beam. There, if I ask you to draw the diagram, you don't have to be very particular about the curvature shapes. They could be right or wrong, I won't be very particular. As long as the overall figure is okay, it's fine. Maybe you can work out the value of the, at the discontinuity, what are the values at the end points and things like that. Simple, this thing you should be able to work out. And then also, there we know that when dm by dx is equal to v. So when shear force is 0, at that point bending moment should be maximum or minimum, or when its area is changing sign. So then that should be reflected in your diagram. But exact curvature doesn't matter. When it's a cubic shape or quadratic shape, as long as overall figure is correct, it doesn't matter if you make the curvature concave or convex. I'll not, because I'm not, it's not a maths course, so I'll not be doing that. Okay. Well, some people do insist. Then after this, then we looked at the problems of friction. So just these topics we have done, not too many, this thing. If you look at your book, it's about 400 pages, I think. So we haven't done too much.